Here we go. Okay, today we're going to start. We're jumping back in the Gaddis book to get rolling again. We're going to hit chapter 21. I'm hoping that you see the sequence the way I see it and how one keeps building off the other, even though the textbooks don't go in the order in which I like. But think about what we just covered. We went from linked list to doubly linked list, and we had nodes that pointed to the next and the previous. Well, we're going to kind of twist those nodes a little bit today. And instead of going left to right, going horizontally, we're going to go vertically. And we're going to talk about this new thing called a binary tree. All right. Once we get started, you're going to go, yeah, I kind of have an idea what this looks like because I watched the other video you had over spring break to get ready for class today. Didn't you? Look at that. 5 thumbs up. I like it. I like it. Okay. What is a binary tree? Binary tree is a nonlinear, it's not horizontal, as we talked about, but each node can point to 2 other nodes. And as we draw these, you'll see instead of going left to right, why we go vertically. Every node but the node has a single predecessor. Oh boy. Why are we doing this? Make searching large sets of data quicker. Okay. One of the things I'm now thinking of is, well, no, wait a minute. If I could point to 2 nodes, why not create a struct that could point to 3 nodes or to 4 nodes or a struct that can hold multiple values? Well, that's coming with this idea that that's something that's coming. All right. To get the party started, we have a pointer. We're going to call this pointer root, not Groot. I am Groot. We're going to call it root. We've just called it head. We've called it front. We now have something called root to get us started. Yeah. Okay. So we have root. Root is going to be a pointer to a node. This node is going to have, in its simplest form, 3 things. Instead of a prev and a next, we're going to have a left pointer and a right pointer in the value. Now, this is just going to slowly grow vertically. Why is this called root? Why is this called a tree? Well, if I spin it upside down, the tree is blossoming out and the root is down here at the bottom. So it actually should be called like an upside down tree. An upside down tree. Some terminology. Once I go to my first node, you'll see that nodes have a left child and possibly a right child. Children might be null. And we have a term called a subtree. And we'll get to some more terminology, some more tree terminology in a minute or two. Instead of head, which was what we use for linked list, instead of front, which we use for queues, we're not going to use root terminology, root, which is a pointer to get us started. Okay, Adam, you good? I see Adam's writing a lot. You
Yeah,
need another minute?
yeah, one more minute, please.
Okay. And makes searching large sets of data. Data was the guy that was on Star Trek, right? No, Star Trek's before all you folks. Okay, I won't go too far. The next thing we're going to talk about is how we're going to use these binary trees. Binary, 0 or 1. We're going one of 2 directions, left or right. And we're going to create something called binary search trees. So I want to build my first binary search tree with the values M, F, R, P, and B. Well, remember before, if I was searching, I'd either start at the beginning and go through until either it was found or I went all the way off the end of the paper. Worst case scenario, I ran off the end of the paper. Well, now we're going to start to build one of these trees. So I'm going to cut searching time down faster. We also looked at not just a sequential search, we did look at a binary search where this list had to be sorted. Now, it doesn't have to be sorted, but we're going to put it in a tree. How do we do it? Well, we start out with M, and M is going to be my first node. Okay, so I'll have a pointer. That root pointer would point to M. Now, as we know in these nodes, we have a left pointer and a right pointer. And as I build this binary search tree, values that are less than go left, which means values that are greater than go right. Okay, my next node, my next value is F. F is going to go to the left. I have M, F, R, P, and B. My F is going to go to the left. So it's going to point to this node. And again, I need to do the drawing before I can start writing any code to fill the tree. How would I fill this binary search tree? Oh boy, I go to here. If it's less, then yeah, I'm hoping this first value is a good first value too, right? I wouldn't want to build a tree with A, B, C, F, G, R, T, U, because everything would just go one line down the right. That would stink. R comes in, it's greater than M. So if I had three items, I should be able to search this tree and find it in two moves. Is this it? No. Less than or greater than. Less than, boom, found it. This stores one item. This stores three items. After the R is P. P is going to be greater than M and less than R. D. Is there a, I want to search this tree. Is there a B? Yes. Less than yes. Less than yes. Boom. Found it. How many items could I store and find it in three moves? How many items could I store and still find it in three moves? Well, this could go to one, this could go to one, and this could go to one. So that's 1, 2, 3, 4. I could store seven items and find it in three moves. Oh, yeah. Seven items and find it in three moves. How many items could I store and find it in four moves? How many items in four moves? I'm at seven. How many more am I adding on? Here's one. 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 I could store how many items and find it in four moves?
15.
Yeah, up to 15 items, right? Add 2, 4, 8. I bet this next line would be sequences and series, pre-calcs. How many could I have in five moves? I took this, added 1 and got to 7. Took this, added 1 and got to 15. How many moves would it take? Or how many items could possibly be stored? 31? I take the 15 and add 2, 4, 6, 8, 10, 12, 14, 16, 31. Yeah. If I had 31 items written this way and I did a sequential search, it's going to take 31 moves. If I did the cut in half, cut in half, cut in half, cut in half, for 31 items, how many moves would it take? So this is a new way to create a binary search tree to help us search and find large sets of data. Whoo, that's the picture. Through it here. We were just talking about that. How many could I find? We kept doing some math. Level 1 stores 1 value. First 2 levels store 3 values. 3 levels store 7 values. Quickly storing a lot of stuff. Okay, questions? Give me that paper. Give me that paper. I'm giving you a list. 5, 8, 3, 12, 9. Build a binary search tree with that. Build a binary search tree for that.
Wouldn't 5 be the root?
Well, 5, nope, 5 is going to be your first number.
Your root will point to 5?
So root will point to 5.
Then A would be your right child.
So 8 would be a right child.
3 would be the left child.
3 would be a left child.
12 would be, and 9 would be
12 would be a right. And 9 would be a right, left. The bigger the list, the more it fills in. The better the root pointer, depending on your data. What do all these point to? Null, as before. No, 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 no. How many nulls? 2, 4, 6 nulls. 6 nulls. Okay, we have a binary tree. Go back to everything we've learned before. If I have a binary tree, what are some things I'm going to look for? Is it empty? What functions can I build to work with this? Is it empty? If not root, that kind of deal, like before, we would have insert. Well, we were just kind of practicing insert. We would have delete. We would have some sort of traverse for printing, for searching, for. So these basic function ideas come back again and again and again and again. All right, let's start with traverse. Pew, 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 pew. Traverse. Oh, there's going to be a couple of different ways to do traverse. We're going to take a look at something again called pre-order. We briefly talked about this before. In order, in post order. Boys, I'm going back to simple examples. In order was the one that was good. 4 plus 3. Pre-order was 3 plus, excuse me, plus 3, 4. Oh my God, what are you doing? Plus 4, 3. Thank you. The numbers are in the same order. The operation just comes in the beginning. And post order is 4, 3 plus, where the operation comes afterwards. So now I'm going to look at this real quick as a binary search tree, and I'm going to use in order, and I'm going to put the plus here. This is going to be the 4, and this is going to be the 3. So I'm throwing this operation 4 plus 3, the in order, onto a binary search tree. Plus 4, 3. I'm going to look at a blank one. I'm going to say that's my node. This is my left, and this is my right. So when it comes to pre-order, it looks like the plus, it's going to be node, left, right. So when I'm working on this and I want something done in pre-order, it's going to be, I said it right and wrote it wrong. Node, node, left, which is the 4, right. Node, left, right. In order, left node, right. Post order, left, right node. You notice here the node, which is the plus sign, is first. The node is in the middle. The node is at the end. So it just moves through just like the plus. But we can visualize this a little bit on a binary search tree. Why are we doing this? Because we're going to do 3 different types of traversing of this tree. And the 3 are the pre, the in order, and the post. And we're going to follow this saying of node, left, right, etc., etc. Right? So let me give you one. And if I can find my example, where's my dooby dooby doo? Let's come up here. We have pre-order, we have in order, and we have post. Taking a look at this tree, the pre-order was node, then left, then right. So the node is 5. I do the 5 first. Then I go left. But my left is a node. So now I would do the node, which is 3. Then I do its left. Its left is null. So I go back up to the node. Its right is null. So now I go back up to this node. So I did the node, left. This was a node. There was no left. There was no right. Again, I'm following node, left, right. Come back to this node. Do this guy. I get 8. Has no left, so I go to its right. I do the node, which is 12. Go to its left, which is 9. Excuse me. It has no node, so it goes back up, goes to its right, and we're done. Excuse me. In order, left node right. I go left first, which is 3. Now that I'm here, I go left. There is no left. So I go back to the node. I already did that. I go to its right. There is no right. So I go back to the node, which is now 5. Come back to his right. I do the left. There is no left. I do the node, which is 8. I go to the right. It's a node. So I go to its left, which is 9. 9 doesn't have a left. 9 doesn't have a right. So we go back up. We now do the node and we check its right and we're done. Do you notice what in order did? In order traversal gives me sorted. Post order, left, right node. Huh. Go ahead, I'll give you 15 seconds to try it on your own. Left, right node. Ba-da-ba-da. Easy. I started a node which is 5, go to its left, which is 3, go to its left, which is null. So I go back and I would put the 3 down after I went to its right, which was also null. Then I go up, and instead of the node, I go right first, which at this node I check left, which is no. Go to its right, which is a node. Check its left, which is 9. Check its left, which is a null. Go back up, check its right. Go back up, display my 9. Go back up, check its right, which is a null. Display the 12. Back up to the node, which is 8. Go back up to the node, which is 5. Do you think another one? Or you got it? Anybody? You got it? All right, let's done with that page. Let's come to this page. So we just talked about some traversing. Let's take a look at delete. Let's do, how we've been doing. Let's do some walkthrough going through delete and see what we have. All right, delete. So I made up a tree. I made one up 15, 7, 3. And I'm thinking of what type of test data might I need? I feel like I'm missing some stuff, but I think we're good. Let's see. According to this, I might want to delete this guy, the 15. Oh boy. I might want to delete the 7 because it has a parent and it has at least one child, possibly 2. We might want to delete the 3, which is down here on the end. So as I go through deleting, I'm saying I want to delete 15. Not only is it head, it has possibly 2 children. It has a 15 and an 18. Excuse me, 15 has a 7 and an 18. How would I work that? What if I wanted to do? So I'm thinking, what are all my cases? 2 children, 1 children, the head, down here on the end, this guy called a leaf. Makes sense. It's called a leaf. How would I go about doing that? Oh boy. How would I delete one child? All right, well, how do I know, how do I know I want to delete 7. So for this first example, we are going to try to delete 7. Man, oh man, oh man, is this going to be a lot of code for to take care of all the situations for delete? What do you think? What y'all thinking we might do?
First check if it's empty, and if it is, report an error.
Okay. Let's just think about this situation right now. What might do? So one of the questions we're going to keep asking ourselves all the time is, do I need some kind of temp pointer? So I'm thinking, I have head, and head points to 15. And where would I, oops, crackers. Where would I go next? This goes down to 7. And in this case, this goes to null. And this goes to 3. And then what? So I want to delete the 7, and this is where we're sitting right now. So temp pointer started at head, so temp pointer is going to get the value of head. And then it looks like we know that it's less than. Again, we're just building a couple of lines of code to get this straight. So if my value is equal to 15, what would I do? If my value equals 7. So right now, val equals 7. So I'm getting ready, and temp pointer is now sitting over here. And I just checked. Val is less than temp pointer's val. That is true. So I come here. So do I move temp pointer? Do I not move temp pointer? Because I now want this guy to be true. So val equals data, data, data. Give me a couple of lines of code that's going on here. Temp pointer is sitting here right now. I know that it's less than. I might even do this. If val is less than temp pointer val, I'm jumping down to here, and I want to delete this 7. I could also do and temp pointer, blah, blah, blah. This guy equals null. Yeah, what if I'm moving left, or what if I'm moving? Oh boy, lots of situations to take care of. So now I come in and say if temp pointers if temp pointers left what would this be? If temp pointers left temp pointers left val equals 7 equals what we have stored as val. What would I put? What do I need to do? I need this guy to jump down to here. And again, we'd have to check and make sure this is null, but we're deleting something that has a single child. Yeah, what if the single child's to the left? What if the single child's to the right? Lots and lots of code's going to happen in here. What is this red line?
Isn't that what you're trying to do as the end result?
Yep. Tell me what to write.
That would be where is the word? Left,
10 pointers, left.
temp left equals temp left
Do I
left.
need, do I need a little more here? 10 pointers left, which is this guy right here. What'd you say is going to get the value of?
Temp pointers left left.
Yep. 10 pointers left, left. Again, I don't want to write blocks of code. I want to start getting these lines of code so that, yeah, this guy, 10 pointers left, which is right here. This is 10 pointers left. That fella right there. That's 10 pointers left. Now gets the value of 10 pointers left, left, which goes to there. So that would take this and skip it down. Again, this is a single child, and we're moving down, to the left. So you can see there might be code where I have to move down to the right. 10 pointers left's right gets the value if it was 8 sitting over here instead of 3. But that would be deleting a single node. Sheesh. Deleting a double node, something with 2 children. How would that look? What if I wanted to get rid of 7, but 7 has 2 children? Well, yeah, okay. I've got stuff drawn here. Help you out. This guy is now going to point to so my question might be, what should go up here? The 3 or the 8? What would go up here? The 3 or you think the 8?
The 8.
Going to be the 8. That sounded like a guess, Nicodemus, but I'll take it. Why? Well, if you look, the higher up we go, it is the 8. We want the higher values up. Okay, so it's going to be the 8. This guy's going to go. So what's going to happen is this guy now has to go to here. Step 1, that guy right there. Step 1. Let's see. So that's going to move that over. Step 2 would be to move this over to here so that the 3 is less than the 8. Fortunately, all of these point to null, because if this didn't point to null, 8's left, I'd have to keep going all the way down until I got a null and then point that farthest down null over to 3. Let's assume temp pointer is pointing to 15 right now. What are the 2 lines of code? I'm going to pause the recording. I'm going to let you try to work it out. And we'll go from there. Anybody have those 2 lines? Anybody? Raise hand, Nicodemus. What do you got?
Temp left right left equals temp left left, and then temp left equals temp left right.
Okay, temps left.
Right
Temps,
left equals temp left.
I'm sorry. Let me back up and go slow. Temp pointers left. That's the
Right.
first step, right?
Yep.
Temp pointers left. It's going to get the value of Go ahead. I think you said it.
And I think I
Temp,
did it backwards because then that would be temp left, right.
yeah. Yep. Then pointers left, which is this, now gets the value of this. 10 pointers left gets 10 pointers left, right. So this guy up here gets the value of that guy. So it points to the 8.
Oh, wait, just a quick question, but if
Go
we do
ahead.
that first, wouldn't we mean we lose the left left? Because it's no longer having anything that points to it?
Question is, once I change this to 8, I lost this whole left side. So is this really step number 1?
Well, wouldn't that be two then?
That's going to be step number 2. This is going to have to be step number 1. Okay, so this takes care of number 2, but the first thing we needed to do was, what you got? This is going to be a good one.
Um, Temps left, right, left equals temp left, left.
10 pointers left, right, left, which is this guy right here. We need to make it point to there. And you may have to say it again. 10 pointers.
Oh, we're pointing to the left, left, right. Okay.
Did I mess this up? 10 pointers left, right, left, which is this guy. We want to point to there. 10 pointers left, right, left. We want it to point to 10 pointers
Mm.
left, left. Sorry, I got these out of order, but I'm glad we caught it. No excuses. It's only been 4 years since I taught this class, but I think I'm doing pretty good overall. So again, is this, man, oh man, delete is going to be crazy to do all of the different ones. Could we do delete? Yep, we could sit here and I could say, Adam, you do this case. Nicodemus, you do this case. Read this case. Delete Joseph. We could break it down and put all these pieces back together. We'd have lots of if statements. We would need lots of drawings to get all these possible situations. Okay. Okay, yeah, I got stuff going on here. I don't know what all I was drawing over there to here to back to there. This was that. Remember, I said if you're going to put this one up, you'd have to keep going left, left, left until you attach that. So you would need some kind of code that just keeps going on and on recursively to get to that point. All right, more stuff. Let's practice again. Okay, I want you to build a binary search tree using these letters. Build a binary search tree using those letters. I'm going to pause the recording. H A R R I what's next? S B U R. Ooh, never realized there was three R's in Harrisburg. Never thought much about it either. G. No, no, no. Questions? Hope you got it right. How many children are there? How many children are there? Take a guess.
9 if we don't count the nulls.
We're going nine. How many parents?
6.
Six. Lots of subtrees. ABG is a subtree. So that was another term we had. What's the height? Five. Could you write code to count the number of children? Parents. Could you write code to count the height? Could you write code to find how many nulls there are? Again, a lot of this is coming back to traversals. Let's pick a traversal. Pre, post, or in. Which one do you want to pick? Who's the hardest one? Post. Let's do post. Post fix. That meant the node came afterwards. Left, right, node. I'm going to pause the video again. Oh, crap. There we go. Resume recording. GBA, should I go through it again? I come down and I'm looking at left, right node. So I go left, left is a null. I exhausted left, so I come back up, go right. Check, no left, go right. Check, no left, no right, go back to the node. Go back to the node, go back to the node. I exhausted H is left, so I come right. I go left. There is no left. I check it's right. There is no right. I come back to the node, which is an I. Took care of this R's left. Check this R's right. No left. Check the right. Go to the left. There's no left. There's no right. So I go back to the node. I exhausted the left. So I come to the right. No left, no right. Node, 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 node. All the way back up to H. Any questions? All right. What do we got going on here? I'm in NIOF now. I'm jumping over to chapter 12. I've done a lot of talking today, folks, and I kind of do apologize. As you know, in the NIOF book, you're going to see all of this, these examples over here, how we have subtrees and going on and deleting them. They talk about one of the most, where is it, popular binary search trees right here. There it is. Dots, dashes, to the left, to the right. Why is this built this? We're going to come back to this eventually. We're going to do some really cool decoding stuff. But your most popular letters were E and T at the time. I, A, N, and M. Binary search tree is built out of that. Some other things that are in here, and oh boy, we're not going to get to everything today. We're going to have to finish some binary tree up, but there are. I'm looking for. Here is an example of a tree. This is called a decision tree. It's called a decision tree. There used to be a game. Can you guess the animal in 10 questions or whatever? Does it live on land? Yes or no? Does it have legs? Yes or no? Four legs? Yes or no? So you could start to narrow down quickly. We're searching using a binary search tree to get to an answer that we wanted to pretty quick. Array representation. Now, with the binary search tree, we're going to use arrays a little bit, but boom, are they going to get hard? They're going to get hard. For example, if I have an array, my array is numbered 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I have location 0, which is O. Location 1, which is M. E goes in 2, 3, 4, 5. And guess what's going to be in a lot of these? Nulls. Nulls. Again, some problems. What if I don't have enough memory? Boy, gonna get into some. I don't know what's going on. So that's that. Gonna come back to that in a second, the array representation. What you see in front of you is something called a complete tree. A complete tree. Every level is filled in completely, except possibly the bottom. Do you notice how it's filled in left to right? Like the last empty ones are over here. And we're going to use these complete trees later. So this terminology isn't going to go anywhere. And we're also going to work with something called a a balanced tree. A balanced tree. This tree is not balanced. Now, how do we get a balanced tree? Well, you notice there's a node missing here. Oh, there's a bunch of nodes missing here. Well, a balanced tree is going to be one where the left subtree. So I'm going to do a subtraction. I'm going to do a subtraction. Okay. If I looked at O and I said, what's the height of its left subtree? What would you tell me? What is the height of O's left subtree? 2. What's the height of its right subtree? So we're doing left subtree minus right subtree. So for O, 2 minus 2 is 0. For M, 0 minus 1, this is a -1. For E, 0 minus 0 is 0. So I can start looking at numbers here. For T, 1 minus 1 is 0, 0, and 0. Left subtree minus right subtree. As long as these numbers are -1, 0, or +1, we have -1, 0, or +1, we have a balanced tree. Is this a balanced tree? I don't know if you can see it or not, but O's left subtree is a 2. Its right subtree doesn't exist, so this is a 2. And already I could say, folks, this is not a balanced tree. Which one's going to be easier to search? A balanced tree or not a balanced tree? Or not a balanced tree? What's E? What's that number we would have for E? I get a -4. That's really bad. That means this is not going to be very efficient. Ones and zeros and negative ones will be. It'll be very efficient. Okay, we did not finish binary trees, but we're going to stop here and get into it a little more next week. Put this in here and in here. And I am now going to talk about, Baba, I need to change my camera because you don't want to look at my hand. I'm going to talk about a project you're going to work on. So I'm going to share and I'm going to go back to our home page and we are in 162. Well, it's not in 162. And you're going to do this big O notation. Okay. You're going to make a project for me that explains big O notation, but you are going to dumb it down. You are going to dumb it down. Okay. I have an attachment. You see your two groups. We should be familiar with everybody, but you can go to class list and get emails. You can spend a little extra time after class today making sure you're connected. Again, Nat is not here. He'll be back. He just had to miss today. Now, what is big O notation? Well, I'm going to stop and I'm going to share this screen. It's a 50-point project. The first 40 points are going to come from a video of some sort that you make to really dumb down big O notation so I can understand it. Content and explanation is 20 points, diagrams 5, presentation 10, appropriate for dummies 5 points. All right. There's a section in the NIOF book. You should start with the section in, I don't know why it won't let me highlight that, to get you started. I've found tons of websites for you to look at to help you get started. But this is going to talk about efficiency of a program. Now, it has to be a video, and the video should be about 5 to 7 minutes long. And if you give me 1 second, I am going to, where am I looking? This was one. Okay, I'm going to pick, yeah, where is it? Here it is. Can you see this? So this group made this presentation. If I go back to the beginning, so you're going to make a video however you want. That was one example. Another example. Let me see if I can pull this up. This group did a PowerPoint, but it's a PowerPoint that runs. I have to be able to run it, and you're talking and explaining it. Let me see if I can get back here and share it real quick. Share a PowerPoint. You can do whatever you want. So as soon as I would hit click, it would play. One semester, 3 guys went out and they were in the woods and made a video hunting for big O notation. And they found different equations and then they talked about the equation. Whatever you want to do, make a video that dumb downs big O notation. If you go to YouTube, you're going to see a whole bunch of them that are boring. I want you to do something fun. Okay, you have 2 groups. I can pull up lots and lots of examples. I just have to go back to 2018 and 2019 and that. But have a little fun with it. But it's something I want to sit down and click play and sit and watch and see if your group can explain what's going on. 40 points are going to be on the presentation. 10 points are going to be on evaluating people in your group. So if there's a freeloader in your group, you evaluate when you get to that evaluation, you evaluate them honestly, and then that's how I come up with the extra 10 points. If two people in the group say so-and-so did nothing, then I don't give them any points for the first 40. Due date. What am I looking for? Due date. Where are you? April 16th. You have a month. You have a good group, you could have it done in 2 weeks. The deadline is 1 month. Questions? Questions? All right. As I said, we're going to come back and spend about 10 more minutes, 15 more on binary trees next class, and then we'll move on from there. I'm going to check out here and stop my video and everything so that if you want, and you already know who's in your groups, right? I have it typed up for you. You can get together and talk for a couple minutes. And otherwise, I will see you next Monday. Again, don't hesitate to email me if you have questions.